Happy morning, students. This is GATE coaching class organized by Erode Sengunthar Engineering College, Tamil Nadu, under the scheme of AICTE Prerana, scheme of preparing SC/ST students for higher education, especially for GATE. For today's session, myself, J. Sridhar, Assistant Professor of ECE, Erode Sengunthar Engineering College, Tamil Nadu. For today's session, I'm going to handle you the network theory subject. Under this, we'll concentrate on the topic of network elements. So this is overview of my today's class. Today we are going to see about what is voltage, current, energy and power, types of networks, network elements, Ohm's law, series and parallel combination of elements, Kirchhoff's law, voltage and current division rule, source transformation, star and delta, vice versa conversion, and problems. So voltage, always a force of attraction exists between the positive and negative charges in an atom. So this is the basic thing which we all know. The energy required, so what is voltage means? The energy required to overcome this force and move the charges through the specific distance is called potential energy. So the potential difference in the potential energy is called the potential difference. The term is called voltage. So the voltage can be defined with the formula of work done mean energy divided by charge, which means work done against 1 coulomb of charge, which is called as voltage. So next, current. So the rate of flow of electrons in a conductive or semiconductive material is measured by the number of electrons flow past a point in a unit time. So I can be defined as Q by T, which is called as dQ by dt, rate of charge with respect to time. So voltage and current can be explained in this way. So say V1 is a voltage in a point and V2 is voltage in another point. So V1, the value of V1 is greater than V2. So which is called as value of the voltage value of V1 is greater than V2. So automatically the charge are flows from the point V1 to V2. So the current flow between V1, current flow can be done in the form of in the point from V1 to V2. So which can be explained as say V1 is a tank which is placed at the top of the building, and V2 is another tank which is placed at the bottom of a building. So automatically pressure difference in the V1 and V2 is high. So V1 is, so the water flows from the tank V1 to V2. Same way, the current flow from the point V1 to V2 will be passes. And energy and power. So before defining the energy, we'll get into power. So power can be written as voltage into current. Power can be defined as voltage into current, and this power will be measured at watts. And energy can be defined as power into time. Energy can be defined as power into time, which can be measured at the term of joules. So there are different types of networks are available. So we can classify, there are 4 networks, classify the networks into 4 types. One is active, or passive elements, active and passive elements. The second one is bilateral and unilateral elements, and the third one is linear and non-linear elements, and the fourth one is lumped and or distributed elements. So first we'll see active and passive elements. So the active elements have the capability to deliver the average power greater than for infinite period of time to the connected devices. Example, the ideal power sources like battery, voltage, everything. And the passive elements which consumes or dissipate the energy stored in the circuit. Example, resistors, capacitors, inductors are the passive elements. Bilateral and unilateral network. In the bilateral network have some voltage to current relationship for current flow in either direction. Any conducting wires, resistors. So these are the example for the bilateral networks, and the unilateral networks. Example, vacuum diodes, silicon diodes, rectifiers. So these are all the example for the unilateral networks. Linear and non-linear networks. Linear elements have the linear VI relationship, VI in the sense voltage to current relationship, which is under the straight line, which is passing through the origin. So linear element obeys the superposition theorem. Example, resistance. So non-linear elements is directly opposite to the linear elements. So the voltage and current relationship could not be defined in the straight line which is passing through the origin, which can be varied at any direction at any time, depends upon the elements. So example for this nonlinear elements are the diode, transistor, xenodiode, triac, ECE-GATE. So all the semiconductor devices comes under this nonlinear devices or nonlinear elements. Lumped and distributed. So small in size. Simultaneous action takes place for any given cause at the same time of instant. So the size is very small, which is compared to the wavelength of the signal which is applied at the input side. So example for this, resistance, inductance and the capacitance RLC elements. Distributed elements are not electrically separable for any analytical purpose. Example for this, transmission line has its distributed RLC throughout its entire length, and comes under the network elements, which is most important part for our topic. There are three major elements used in the electric circuit are resistance, inductance and the capacitance. Let us see about all the three elements in a detailed manner. So first we'll go with the resistance. So here resistance, there is no more collision of electrons within this material, which is made up of any metallic conductors, which is free flow of current. There is no drop. Under the resistance, which is resistance value is 0 ohms. The resistance value is not equal to the 0 ohms. Due to this physical property of the material, collision of the electrons with the atoms of the material takes place, which drops the flow of current. The flow of current is resisted by the value R, and the drop of the potential across the material. So the resistance, when we include a resistance inside a circuit, which is used to resist the flow of current and will drop the voltages across this resistance. And finally, inductance. A wire of certain length is twisted into coil to form a basic inductor. So which is shown in the figure. So when we pass through the current through this inducting element, when time varying current changes through the inductor, a flux will change. A flux will be produces through the, and when the current changes instantaneously, and the produces flux will also changes instantaneously according to the Faraday's law. There will be some voltages induced inside the coil, and which is given by L is equal to V is equal to L into d by dt. Note, for the coil will produce the flux changes when the current changes instantaneously. When we pass a DC current through this through the inductance element, di by dt is equal to 0. So the voltage across the inductance will be 0 as a short circuit. And the capacitance. So it has two conducting surfaces separated by a dielectric material. So the capacitance is the amount of charge a capacitor can store when a voltage is applied across to it. So the formula of capacitance C is equal to Q by V. So Q is charge stored inside the capacitance, and V is voltage applied to the capacitance across. So next, Ohm's law. Ohm's law states that in a metallic conductor at a constant temperature in a zero magnetic field, the current flowing is directly proportional to the voltage of the conductor is inversely to the resistance of the conductor. So this V is directly proportional to I. So to remove the proportionality symbol, we'll introduce a constant value is R. R is the value of resistance of a conductor. So V is equal to I into R. So VI graph of the shown here. So is nearly increasing when the voltages increases. There are some limitations under this Ohm's law. Limitation is the conductors should be metallic conductors. So there will not be any the Ohm's law could not be applied to the other than metallic conductors, and this Ohm's law could be applicable only when the temperature is constant. When the temperature is constant. So this is the limitations of Ohm's law. Series and parallel combinations of elements. So under this, series and parallel combination of resistance. So here R1, R2, R3 are the three resistance which is connected the series combinations. So the total resistance of this circuit can be calculated with the formula of Rs equal to 1 plus R2 plus R3, which is summation of individual resistances. So series resistance of a series combinations can be calculated by sum of individual resistances. So here the total resistance, the value of total resistance is always greater than the individual resistance. So Rs is greater than and R3. So this is the property of this is the formula to calculate the series combination, total resistance in a series combination. And the second one is parallel combination. So here R1, R2, R3. all the three elements are connected in a parallel. So the total resistance in a parallel combinations can be calculated with the formula of 1 by RT. RT is total parallel resistance, resultant resistance. So 1 by RT is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So here the total parallel resultant resistance value is less than the individual resistance. So this is the property of parallel combination. So the total resistance is less than the individual resistance. So one more thing in the series combination. So it's here the series combination. In the series combination, the current flow towards through the R1, R2, R3 are same. The current flow through the resistance R1, R2, R3 are same in the series resistance combination, and here voltage across the R1, R2, R3 are same in the parallel combination. So here current is a constant parameter. Here the voltage across the elements are constant parameter. In a series circuit, voltage across the individual elements are different. So say for example R1 with the drop of V1, R2 with the drop of V2, R3 with the drop of V3. So when we sum R1, V1, V2, V3, which should be equal to the total applied voltage. In the same way, parallel combination, here the current flow element R1 is I1, R2 is I2, R3 is I3. So when we sum I1, I2, I3, which should be equal to the total current flow through the circuit I. So this is the property of series and parallel combination. Next, series and parallel combination of inductance. So here inductance will be connected with 4 ways. There are 2 inductance L1 and L2 connected in a 4 different ways, which is called as series aiding, series opposing, parallel aiding, and parallel opposing. So the dot is indicated to calculate the mutual inductance. Dot is indicated to the mutual inductance value between the L1 and L2. So here dots are in a same place, which means current flow towards the dot in a same direction, which is called as aiding. So L1 and L2 is connected in a series combination. So which is called as series aiding. The total inductance value can be calculated with the formula of L1 plus L2 plus 2M. M is mutual inductance between the L1 and L2. And the second combination is series opposing. So here L1 and L2 are 2 individual inductance which is connected in a series format, and here concentrate on the dot, place of the dot. Here dot is placed current flow towards the dot, and here current leaves through the dot. So the dots are at the opposite direction. So this is opposing and resist. So the inductors are connected in a series. So this series opposing. Well, inductance for the combination is L1 plus L2 minus M, because this is dot L1 plus L2 minus parallel. Parallel AD is L1 L2 is connected parallel manner. Here place of the dot is current flow in two inductance, current flow towards the dot is the state action. So aiding and the reference is connected in a parallel manner. So this is parallel aiding combination. So the total inductance can be calculated with the formula of L1 into 2 minus m square divided by L1 plus L2 minus 2m. So here m indicates that mutual inductance L2. The next one is opposite. L1 and L2 are connected in a parallel way, and the dot in the universe current flow towards the dot at L1. Current leads towards the dot at L2. So L1 and L2 are in the opposing manner. L1 and L2 connected in a parallel combination. So equivalent resistance can be equivalent calculated with the formula L equivalent is equal to L to L2 minus m square, the whole divided by L1 plus L2 plus 2m. So m is mutual inductance between the L1 and L2. So next one is series and parallel combinations of capacitance. So C1 and C2 are two individual capacitances connected in a series manner. So the total capacitance value can be calculated by 1 by Cs. 1 by Cs is equal to 1 by C1 plus 1 by C2. And the parallel capacitance C1 and C2 is connected in a parallel manner. The parallel capacitance value can be calculated with the formula of Cp is equal to C1 plus C2. So here in a series capacitance, the total capacitance is equal to is less than the individual capacitance. So here the total resultant capacitance value is less than the individual capacitance. In a parallel combination, the total resultant capacitance is greater than the individual capacitance. So this is the combinations of series and parallel for a resistance, inductance, and the capacitance elements. So next we'll concentrate on basic laws. Law. So Kirchhoff first law is Kirchhoff current law. So Kirchhoff current law states that for any node or junction in an electrical circuit, the sum of the current flowing to the node is equal to the sum of current flow out of that node or equivalently. Or otherwise we can define as the algebraic sum of the current in a network of a conductor meeting point is 0. So here there will be a circuit with the branches of 1, 2, 3, 4, 5 branches. So here I1, I3, I5. All the three branch currents are a current flow towards the node. And I2, I3 branch 2, branch 4, current flow away from the node. I2 and I4 current flow away from the node. So this can be, the equations can be written as I1 plus I3 plus I5. All the three currents are current flow towards the node, which is equal to I2 plus I4. So these currents are flow away from the node. Or otherwise we can write I1 plus I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. So current flow towards the node is taking in the positive direction. Current flow away from the node is taking in the negative direction. So all the total currents are all the total in junction point is 0 or node point is 0, which is called as Kirchhoff's current law and Kirchhoff's voltage law. This law is also called as Kirchhoff's second law, which is defined at the loop. Kirchhoff, the direction, sum of the potential differences around any closed loop is 0. So here V1, R1, R2, R3 are the three individual resistance are connected in a series manner excited with the voltage V. So current flow through the closed loop is I. So depends upon the Kirchhoff voltage law, we can write V1 is equal to V1 plus V2 plus V3. So sum of the individual drops is equal to voltage rise inside the closed loop. So V is equal to V1 plus V2 plus V3. So V can be written I into R1 and V2 can be written as I into R2, V3 can be written as I into R3. So which is replaced here is equal to I into R1 plus I into R2 plus I into R3, which is Kirchhoff's voltage law. Next one is voltage division rule. So here voltage division rule is applicable only at the series circuits, which could not be applied at the parallel circuit, because in a parallel circuit voltage across the individual elements are same. So which is applicable, voltage division rule is applicable only at the series circuit. So here R1, R2, R3 are three individual resistance which is connected in a series circuit, and the voltage drop across the individual resistance are V1, V2, V3 respectively, and the circuit is excited with the voltages V. So the individual voltage can be calculated with the formula V1 is equal to total voltage V into R1 divided by R1 plus R2 plus R3. And V2 can be written as V into total voltage V into R2 divided by R1 plus R2 plus R3. V3 can be written as V into R3 divided by R1 plus R2 plus R3. So on the whole, this formula can be written as individual voltage is equal to total voltage into individual resistance divided by the total resistance, which can be says in a common manner. So individual voltage drop can be written as individual total voltage into individual resistance divided by the total resistance. So we can calculate the individual drop across the each and every elements. Next one is current division rule. So this current division rule can be applied at only on the parallel circuit, which is not applicable at the series circuit, because in a series circuit total current flow throughout the individual elements are same, so which is applicable only to the parallel circuit. So here R1 and R2 are two resistance connected in a parallel and which is excited by the voltage V, and the current flow through the circuit is I. Total current flow through the circuit is I. And the individual currents can be calculated with the help of current division rule, and the formula is individual current is equal to total current into opposite resistance divided by the total resistance. So So here we'll calculate I1 voltage, sorry, current flow towards through the resistance R1. So I1 is equal to I into R2 divided by R1 plus R2. So opposite resistance for the R1 is R2. So R2 divided by total resistance R1 plus R2. Similarly, I2 can be calculated with total current I. Opposite resistance of R2 is R1 divided by the total resistance R1 plus R2. So this is current division rule among the parallel circuit. Next one is source transformation. So here voltage source can be converted into current source, and the current source can be converted into voltage source Y. So here we'll use voltage source is always connected with the series source resistance, and the current source is always connected with the parallel source resistance. So here current source can be modified into the voltage source, and voltage source can be modified into the current source in this manner. So voltage source can be converted into current source with the formula of Is is equal to Ds by Rs, and the series resistance could be connected in a parallel manner, and the current source can be converted into voltage source with the formula Vs is equal to Rs into Is, and the parallel resistance is connected in a series manner. So this is the thing which we need to remember when we transfer the sources. And the next one is star to delta conversion. So this is the delta conversion which we all know, and this is the star connection which you all know. So the delta connections can be converted into star with the help of R1. So here 3 nodes are there, 1, 2, 3, and between the 3 nodes 3 elements are connected, RA, RB and RC. So which is converted as star source, which is converted as star connection R1, R2, R3. So the value of R1 is equal to RB into RC divided by RA plus RB plus RC. R2 can be calculated as RA, RC divided by RA plus RB plus RC. R3 can be calculated as RA into RB divided by RA plus RB plus RC. So this is the formula to convert delta into star connection. And the next one is star to delta connection. So here R1, R2, R3 are the 3 resistance connected in a star connection, which could be converted as delta. So the resultant delta resistance values are RA, RB, RC, and this could be calculated with the formula of R1 plus R1 into R2 plus R2 into R3 plus R3 into R1 divided by R1. RB can be calculated as R1 into R2 plus R2 into R3 plus R3 into R1 divided by R2, and RC can be calculated as R1 into R2 plus R2 into R3 plus R3 into R1 divided by R3. So here we can compare the formulas. Here delta to star conversion, denominator is the constant parameter. See, compare all these 3. Denominator is the common values. So here star to delta conversion, concentrate on these 3 formulas. Here the numerator are the constant values. So this can be which can be remembered easily. The formula can be remembered easily. So here we'll get into some problems. A connection is made consisting of resistance A in series with a parallel combination resistance B and C. The three resistance of value of 10 ohms, 2 ohms are provided. Consider all possible permutations of the given resistance into the positions of A, B and C. Identify the configurations with maximum possible overall resistance and also the ones with minimum possible overall resistance. The ratio of maximum to minimum values of the resistance up to 2 decimal place is. So the problem is, we'll explain the problem first and we'll get into the solution next. So here there are three resistance are available: 10 ohms, 5 ohms, 2 ohms, which we need to connect with the maximum resultant value and the minimum resultant value. And the given combination is A is a series resistance, B and C will be connected in a parallel manner. So what we need to calculate is, we need to calculate or we need to find the maximum possible overall resistance and the minimum possible overall resistance with the different permutations and combinations. So finally we need to calculate the ratio between the maximum resultant and the minimum resultant value of the resistance. So the maximum can be calculated when the 10 ohm is connected in a series. So automatically 5 ohms and the 2 ohms are connected, should be connected in a parallel like this. So the 10 ohm is connected in a parallel and the 2 and 3 ohms are connected in a series.